A long time ago, I introduced in our Scout and Code software packages a simple timer that allowed to execute measurements and do some simple fittings afterwards and store the results. So you could realize a time sequence of measurements and fit results. In the meantime, I introduced scripts and triggers, and in a very simple example today I will show you how to use those tools together with automation. The goal is to develop a system that simulates the output of a traverse measurement system, generates the same spectra as if they were measured, and I will use this tool later on in another video when I discuss the bulk analysis mechanism. Here is the start configuration of code, and I would first like to do some very simple manipulations of the view so that we have some space for components that I will introduce. So I will open the list of view elements. I have shown that before how to do that. I will delete all the view elements and generate a vertical color gradient which covers the window in full width, so that will look like this. The settings for the timer can be found in the options, so we can go to File, Options, Automation, Timer, Parameters, and you can set the interval. That means how frequently is the timer event fired. In this case it's 1000 milliseconds. Every second there is a timer event. You can set a maximum time when the timer will stop automatically. You can have the timer started when you load the configuration automatically, then check the auto start option. If you want to repeat the timer sequence, activate the cycle checkbox, and if you want to log results in a text file, you can activate the logging file here. That's all. Actually, we don't want to use this dialog for setting the timer properties, but instead we will use scripts, which are much more flexible than just firing a timer event every now and then. So let's do the first script. Scripts are view elements, so we have to open the list of view elements, select the script object, which is here, and generate one more, and we can call the first script that we are going to write start. This will start the automation timer, and every script, if you edit it, has already a name, the name that we specified. Right now it has a description. We can just call this start the time sequence, can be any text here, and then you can have a series of script lines. Every line is one command, and one of the possible command is called start automation timer. That will start the timer as soon as we click, and in order to see the timer activity, we can generate another view element, which is called, let me see if just find it, which is called automation button. That is also an action script, so we can start and stop the timer using this button, but we can also just use it to display how the timer is doing. So I set it a little bit larger, and what we now see here, we see a time marker here, and when we start the script, click on the start button here, you should see that every second we get an update of the time sequence. So right now we have no script to stop the timer, but if you click on the timer itself, on this timer view itself, it will stop, and you can also start the timer here. So actually we would not need a real script to start and stop. We can just click here and click another time to stop it again. Okay, but we can also generate another script to stop the timer, and we will add some more commands later on. So I will now do that. Press E, gives us pressing E gives us the view element list, and we can just move the start script a little bit to the side. Let's move it at 60%, 10% on the top, width of 20%, and height of 3. That should be nice. And then we can duplicate that, call the new one stop, position it 5% below, move it up here in the list a little bit, and then we can edit this. We can change the text to stop, time sequence, and change obviously also the thing that happens, which is called stop automation timer. So let's try that out if it works. Update should bring us the tools here. Let's watch the timer. When I click on start, it starts at 0. Now it counts up, and if we stop, it should stop. That's fine. So let's now add another command to influence the timer in the start script. We can edit this script directly from here, pressing the Control key and clicking on the script. Before we start the automation timer, we can change the time interval, and there's a command called set automation time interval, if I remember it right, and then we have comma, and the parameter is, let's say, 300 milliseconds. That would be now a faster timer. So if I press start now, we should get an update every third of a second roughly. So now we have a little bit faster timer events. Okay, for the following exercises, we also need a visualization of what the program does, a kind of status indication, and we can use a label in the view to display some text, and then we can use scripts to modify that text. Let's generate a label in this list of view elements. We can generate a label called let's see, label called activity. Let's start it at 5% top and bottom, and the label should have no text initially, almost no text. And so this would be the label, and when we execute the start sequence command, we can use the script command set label. We have to specify the name, activity, and yeah, let's already use the final text doing measurements. Maybe you remember we want to write a tool that simulates a measurement system that produces measurements at certain positions of a traverse system. So we can set the label to doing measurements, and then let's see if it works. If we press start, we can see here this text. Unfortunately, if we press stop, the text doesn't change. So what we have to do is we have to give it a new text, set label, activity. Let's use the text idle. That means nothing is happening right now. So when we start the timer, timer runs. If we stop, it says idle. That's fine. That's already a nice time sequence. So now we have to do something. And actually what I would like to do is I want to count measurement positions from 1 to 32, like it would be a kind of thin process measurement system doing the reflectance measurements in the simplest case. So we need a variable that we can use for counting. And actually the way to do it is to introduce a master parameter. So what I will do now is to introduce a master parameter called position index. Let's say we go to the list of master parameters, generate a new one, call it position index. We want to use it as an integer number, so the decimal should be 0. And it would be good to see this number in the screen, in the view, so on the screen, sorry, and we can give it the name position index here as well, and maybe it should be at position 10. Let's check if we can see it. Position index. Okay, maybe the width can be a little bit shorter. Okay, that's the variable that I'm going to use for counting. And at each timer interval, at each timer event, there should be an increase of this number until we reach the highest number, 32. In order to do something at the timer event, we need another component called the trigger. Triggers have been introduced as real physical triggers with spectroscopic hardware, but we can also use it for just software solutions. But we have to generate a trigger object in the list of spectrometers. That's just the historical origin of this. So we go to the list of spectrometers. We don't need a real controller of a physical system, but we just take the more or less abstract trigger here. Sorry, there was already one. I will delete it to start with a new one. Okay, that was actually the one that existed already. And a trigger does the following. It takes, when the timer event is fired, each trigger is asked to check its own conditions and to do something if the condition is satisfied. The condition here is the following. There's a formula that computes a value. In this case, it's just the master parameter position index that we had defined, and this value is compared to a threshold value. In this case, this is 31.5. I will come back to that in a moment. And whenever this number here, position index, is smaller as this number, smaller than this one, this script is executed. And the script name in this case is timer event. We don't have a script right now of that name, but I will generate one in a moment. If the number is larger than the threshold value, then another script is called, and this is the script stop that we have already. So what we should do now, in order to use this trigger element, we have to define a so-called timer event script. So we go to the list of view elements. Actually, we can copy one of the scripts, like the stop script, and duplicate that. We can call this timer event. position it 5% below, and then edit the script. Let's call this timer action, or the description at least. And what it does, it should increase the counting variable by 1. There's a command called set master parameter, and the parameter that we want to change is position index, and the new value is the old value plus 1. So that's what should happen at the timer event. We can check if it works. So if I click here on timer action, the position index is really increased. This is the manual version, but if the trigger also works, this should now go also automatically if we start the time sequence. So let's hope. You can see that the position index is counted, and if it's above 31.5, then it should stop. Okay, that's the last position, and then it stopped. Maybe the stop time sequence should also be changed in order to, in a way that the counting variable is set back to 0. So we are back to at the start. So set master parameter position index 0. If that is executed, then we go back to 0. So let's start it again, just to see if the counting works correctly. So if we arrive at 32, actually it's 0. So the timer action increases the index by 1, and actually we could yeah, let's test that. Let's test that in a moment. Now we need another mechanism. Actually, I want to generate optical spectra. So we need to be able to store the optical spectra automatically, but first we need to create some. I want to use a very simple example. We just take a simple layer stack of a nickel chromium layer on glass. The nickel chromium layer will be defined, the material will be defined as the master model that I had discussed before, and we also use the float glass. So I will do that rather quickly. So let's go to the layer stack definition and just compose a new layer stack based on a thin film. That will be the nickel chromium one, and the nickel chromium layer, and a piece of glass underneath. We will take the float glass model. That's in the section that's here, the float glass model. We can take 4 millimeter thickness, and we will use the nickel chromium, the nickel chromium blocker layer, which is here. And let's start with a thickness of 50 nanometers. The nickel chromium master model has an oxygen parameter that goes from 0 for metallic nickel chromium to 1 for fully oxidized, and it can be in between. So we can, in our model, we can change the stoichiometry of the nickel chromium material and the layer thickness, and those are the two parameters that I would like to have flexible. So we go to the list of fit parameters and declare two fit parameters. It's the oxygen content of the nickel chromium blocker and the thickness of the nickel chromium layer. So let's put the oxygen range from 0 to 1 and the thickness, let's say, from 0 to 100. Okay, that's the variation of the model. Obviously, we have to tell the program where we want to compute a spectrum. We have to set the range, and I just want to concentrate on the range 380 nanometers to 1000 nanometers. That's what you can easily get with a spectrometer for production control. Fast measurements on the traverse system. Let's take 200 points and now go to the spectrum that we want to compute, the reflectance spectrum. Let's say we take 8 degrees mixed polarization. Recompute this spectrum, and then finally set the spectral range from 0 to 1. Okay, so that's the spectrum. We can display the spectrum on the screen. Sorry. Okay, and we can also display the fit parameters. Okay, let's move the fit parameters down here and the spectrum to the right. Maybe we can do a little test. Okay, the spectrum changes when I change the stoichiometry, and the spectrum changes also when I change the thickness. Okay, now we can define a little scenario. How should the thickness changing with position on the glass? We have the position index that we can use for computations, and what I would like to suggest is that we have a slight, or that we have a stoichiometry change with position. And we have a thickness change with position, and later on I told you I will use this example to compute spectra for a so-called bulk analysis mechanism, which I will explain in a later video tutorial. But I need a variation with position in order to be able to fit that later on. So we want to have a change with position so the fitting is not so boring. So what I can do now, I go to the list of fit parameters, and instead of having a downhill simplex variation for automatic fitting, I press F4 to go backwards in the sequence of possible variations, and when we have an empty cell here, we can enter a user-defined expression. And for the oxygen concentration, or the oxygen parameter of the nickel chromium, I will use this expression. I will use the position index as a variable, and I would like to divide that by 100 so that we have a linear increase, a linear variation, linear variation of the oxidation parameter of the nickel chromium layer with the position index. For the layer thickness, I would like to have a little bit of more variation, so we can take a sine function with an amplitude of 10 nanometers. Sorry, I should concentrate a little bit more on my typing. Again, we use the position index as a variable, and we can divide by 5. So we cover a certain range of angles of sine arguments here. And so these user-defined functions now give values for the thickness and the oxygen content of the nickel chromium layer. And when we go through the sequence, we should have an automatic variation. Each position gets a different thickness and a different oxidation state. So these are the demo spectra that we should cover. And what we should do now is, well, we should have an automatic export of the simulated spectra, and we can do that at the timer action, and there are script commands that can do that. Okay, there I open the timer action sequence, so we increase here the position index. Actually, what we should do then is we should update the model. We have a new master parameter now, so we need new thickness values and new oxygen concentration values. And maybe we should update the graphics also. And then we should have once we have computed new spectra, we have an automatic export of simulated spectra to CSV files. Okay, when we do this, the code software will write the spectra automatically, so it will select a spectral name automatically, and it will save it to the automatic folder in the database, actually in the spectra subfolder of the database. But we can override that. Before we start the time sequence, we can now tell the program where to store the spectra. Actually, I would like to start with entering a sample name. So there's a script command called edit sample description, which will open the dialog to enter a sample name. And then we can also set the path for automatic spectrum export. And this is called, actually we can call this C, we can use the folder C temp spec. So in this folder we will write the spectra. Actually what I will have to do, just a second, I do that, I will have to generate this folder. Okay, it should now exist, and we can take a look later on what happens in this folder. Actually, it should be here. We can open it already, and we can inspect if spectra arrive here in this folder. So now we are already in the position to press the start sequence. So let's see, we can give the sample name test for the beginning. Now the spectra are saved, hopefully. Okay, let's see what has arrived in our folder. Okay, there's one file. We can check how it looks like. That's a CSV file with wavelengths and the reflectance values. That's okay, that's what we need. But there's only one file actually, and I expected that we would have 32 files. And well, what you can see here is we have an automatically generated name using the sample name, the name of the spectrum, and then there are 3 zeros, which are usually denoting the X, Y, and Z coordinate of the measurement position. And obviously here we wanted to have a different position on the glass, but the code software doesn't know of different positions on the glass. So there's one step missing in order to generate the wanted spectra. We need to tell the code software still how the position Y of the measurement of the data acquisition is obtained from the position index. So we have to compute this number from the position index. And actually it would be good, we need that function a few times. It would be good to do that in a separate script which computes the Y position of the measurement from the position index. I will generate that script first, and then we will try if it works. So let's go to this sequence. Let's go to the view and edit or duplicate the timer event script and call this, we can call the new script update traverse position. That's the name of the script that we have to write. Let's put it here a little bit higher, directly below the timer event. This is compute traverse position, and we now have to use a new command, a new script command, which is called set sample position Y, and after that, after a comma, we have to specify the way how we want to compute that. Let's take an offset of 50. In that case, that means 50 millimeters times the position index. And if position index is counted from 1 to 32, this should be 150, 250, 350, and so on. So we measure in 10 centimeter steps or 100 millimeter steps. Okay, we can now use this script whenever we need to update the traverse position. We definitely need it here in the timer action. So when we have changed here the master parameter, the position index, we have to call this script, and calling a script means we have to use a so-called object command. We have to specify the name of the script or of the object that we want to call, update traverse position, and we want to execute this command. So whenever you want to call a script within another script, you have to use the object command, specify the name of the script, and the action execute. So now when the position index has changed, we want to recompute the new position. We also want to do that to be safe at the beginning. Actually, we should have here the command, I think I forgot, the command set master parameter position index 0, that's the beginning, and object command update traverse position execute. And since I'm going to need that again, let's copy that, because at the stop sequence we also have a timer, a position index change, and we should compute the new quantity here. Just in case, I think it would be good to update the whole model and to update the graph. Let's just check stop sequence. Yeah, and okay, now it would be good if we could check also the Y position, the traverse position, and there's a way to retrieve this number from the model using an optical function. So we have to go to the optical function list and specify a new one. And some global numbers can be obtained using the object name global, and I think if I remember correctly, sample position Y gives the traverse position of the current, yeah, the current traverse position. Let's see what kind of value we get. Okay, that doesn't seem to work. Let's see if we start the timer. Oh, sorry, I forgot. We have to display this optical function value. Oh, it's already running. We have to display that in the view. I hope it will work. This is the Y sample position in millimeter on the traverse, and we should have that at the left position 10 and 25, basically underneath the position index. That would be nice. Let's check if that looks nice. Sample position, okay. Let's now start the time sequence again for the test sample. So the position here is counted or is increased in parallel to the position index counting variable. So that's fine. And what I hope now is that we get also 32 files in our folder. Starting here, I think this one was the one that I had generated before, which is not correct, so I will delete that. It will not be generated again. And so we have at the Y positions, or the traverse position 150, 250, and so on, we have spectra, and altogether we have 32 spectra for 32 positions. That's the tool I wanted to generate in this exercise. So we can just let it run once more to see how it works. Let's say we can call it sample ABC. We go through all the positions. For each position, one spectrum is generated, and later on, let me just check if okay, the Explorer decided to start once more. I guess wrong clicking, sorry. So now we have sample ABC, and here we have the 32 spectra for this sample, and I guess that's enough for this tutorial. I have shown you how to use scripts. I did not give you an overview on all script commands. There are many script commands that you can use. Yeah, basically you have to read the manual in order to get an impression what you can do. Actually, for me, it's very easy to generate new script commands. So if you need something and you don't find it in the list of existing commands, just tell me and I will try to generate a new script command for you matching your needs. So this tool now produces the spectra that I will need in another tutorial about what is called bulk analysis. That means the analysis of many spectra that are generated by measurement systems using parallel computing. That will be the next tutorial that I will develop during the next weeks, I hope. Thanks for today. Goodbye.